All are true, and it's a tautology, right? Then I will go to logical equivalences. Now, logical equivalences means, now here you have, don't put this 0, 0. Every time put true, 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 false, false, true, false, false. Don't change the order. The order should be in the same way. Now, equivalence means if two columns, if you get the truth values of two columns equal, that table is known as logical equivalences, right? I will send this slide after editing, and I did logic I did. Introduction to predicate logic. That is limitations of propositional logic. Propositional logic does not allow us to conclude the truth of all or some statements. Hence, some valid arguments cannot be concluded or translated into purely propositional logic. It is not possible to mention properties that apply to categories of objects, or even about relationships between those properties. Every computer connected to the college network is functioning properly. Computer science lab is functioning properly. However, it is not possible to find out the truth about whether business lab is functioning. Predicates. A predicate is a statement that contains variables, predicate variables, and that may be true or false depending on the value of these variables. Now, example, P of Q, X, denote the statements X greater than 10. What are the truth values of P11 and P5? Now, P11 is equivalent to the statement 11 is greater than 10, which is true. Now, if they say X is greater than 10 is true, then for 11, 11 is greater than 10, which is true. P5 is equivalent to the statement 5 is greater than 10, which is false. Because we cannot talk about the 5 because we are not aware the value of X. Now, quantification means when the variables in a propositional function are assigned values, the resulting statement becomes a proposition, which could be either true or false. Another way to create a proposition using quantifiers, there are 3 types of quantifiers: universal quantifier, existential quantifier, and uniqueness quantification. Right? Universal means universe of discourse is the set of entities we are talking about when using a sentence, also called domain of a discourse. Now, a discourse means, now we can define the domain, right? Now, if I am defining the domain as set of natural numbers, then all these natural numbers belongs to this discourse, and it is the universe of discourse. In using 1a, the universe of discourse can be all human beings, and the sentence is most certainly not true, or it may be a restricted set of human beings, and the sentence may very well be true. In 1b, the universe of discourse has been explicitly restricted by the adjacent in this room. One is everyone, 1a is everyone is happy. That means this is in the room, if everyone is happy, it is known as the universe of discourse. Everyone in the room is happy, right? Then, now here, everyone is happy means not in the room, even outside the universe can be considered as outside also. Now in B, if you take everybody in the room is happy, that means we have to consider only the people inside the room. Now normally universal quantifier means you put A upside down. A universal quantification is a quantifier, something that tells us the amount of quantity, meaning given by or for all. Now, if you are talking about all, we can put A upside down. That means now here you can say for all x p of x, for all x p of x is read as for every value of x, p of x is true. Translated into English language, the expression is understood as for all x, p of x, we can specify later that p of x holds. For each x, p of x holds, or for all x, p of x holds. And x means all the objects that we have to define the universe. X is in the universe. Now, all cars have wheels. Could be translated into the propositional form all x px, where px is the predicate denoting x has wheels, and the universe of discourse is only propositional by cars. Now here we are talking about cars, and we say p of x is x has wheels. Now existential quantifiers means, this is universal, they are now if you join with and, or if all the elements in the universe of discourse can be listed in the universal quantification for all x px is equivalent to the conjunction p of x1, p of x2, p of x3 and p of xn, or in the above example for all x px, if we knew that there were only 4 cars in our universe of discourse, C1, C2, C3, C3 and C4, then we could also translate the statement as P of C1, P of C2, P of C3 and P of C4. Existential means not all, only some. And existential quantification is a quantifier, something that tells us amount or quantity, meaning there is at least one or for some, not all. So that this is the symbol. You can say there exists x, p of x, there exists x, p of x is read as some value of x, px is true. Someone loves you could be translated into propositional form. There exists x, p of x. That is, p of x is the predicate meaning x loves you. The universe of discourse contains, but is not limited to, all living creatures. So here you have to discourse the universe of discourse. These are the people inside this circle. Then existential quantification is connect with all, because here we are not talking about all, we are talking about some, right? Then you can connect with this with or. Now this slide, I will do it for the next day school also, because I know that the rules and these things are not clear to you, right? So I will do this slide again. Now I will go to functions. Can you see the slide? Functions.
Yes, madam.
Now functions means, now normally you can think a function as, now we have some fruits. Then these fruits are put into some machine and we make a cordial or a jam or something, whatever we want. So if we put, we will say mangoes. So the machine does it. It converts that normal mangoes into cordial, and the input is mangoes. Output will be either cordial or a jam. It's on mangoes, but it's not the appearance now. Normally we put the fruit, then something different comes out, but the name has the same name. Now a function means, a function denote it by f. From a set A to a set B is a relation from A to B. For each element, simple A in capital A, now there are two sets here. There is an element B in capital B such that A comma B is in the relation. And if A comma B and C comma D are in the relation, then B is equals to C. Now the set A is normally known as the domain. The set B is normally known as the codomain, right? Now normally D is the domain such that f of x and x should be belongs to D. Now D is domain, x is a value. Now here, what type of normally options. I have taken the wrong slide, I think. Can you see this? Now this is the one I said. Now input, process can be a machine, then the output, right? The appearance of the input and the output is not the same. In mathematics, you call this the input. The machine, the process is known as the function and the output. That means now X will say this machine does, what this machine does is, anything that comes from the input, it will add to and gives an output. Now the function, the process is fx, right? So what is the process is x plus 2. That means if you put 1 into the machine, then 2 will be added, the output will be 2. Function in mathematics, an expression, rule or law. Now, this is known as the rule or the law or the expression that defines a relationship defines a relationship between one value, the independent variable, and the other variable, dependent variable. Now, this is the x is the independent variable. This is the dependent variable. Now, normally y equals x plus 2. It's like y equals, now this is a graph. X is the independent variable, y is the dependent variable. So it is transformed by the function or the machine or the rule. Normally this is known as an expression, rule or law, right? Now here, normally when we put values from the input, that is known as the domain. Then from the rule or the process, you get some values. Those are known as outputs or range. But every time we are difficult to find the range or the output. So normally we have a new set known as codomain. Codomain means it's also a set, a larger set than the output set or the range or the image set. It also contains other values also, and also contains this output set. The three main points you need to define a function is domain, codomain, and a rule. Now I think to understand about the range and the codomain, it's little difficult. So from a input domain, according to the rule, you will be getting some values, right? That is known as the image set or the range or the output. But in problems, we are difficult to find the input, the range. So what we do is we look at some values of the range, the starting point and the end point, and we define another bigger set than the range. In that, you get the range as well as other values also. Now, if I consider the image set is 1 to 10, right? Now, if I ask the students to write the image set, if there are 50 students in the test, they have to write only one image set. But if I ask them to write codomains, there will be, according to this number of students, there can be codomains, right? Then now consider like this. Now image set is 1 to 10. Now I can define a codomain minus 100 to plus 100. That means within minus 100 to plus 100, the image set is also included. Can you understand that? Now here it say, all the outputs you get is known as the image set. Codomain is a set larger than the image set. Is it clear? If it's not clear, tell me now. Is the range and the codomain is clear to you? Now, if I tell the image set is a closed interval 1 to 5, can you suggest a codomain for that? Yes or no? My image set is 1 to 5, closed interval 1 to 5. Can you suggest a codomain? Now there are 34 participants. So there should be 34 codomains. If you can't understand that, let me know. Difficult to understand? Yes or no? Why all are silent? Why you all are silent? Shall I go to the next slide? Then sum and product of functions. Now, normally functions are denoted by simple letters. Let f and g be functions from a set A to a set of real numbers R. Then the sum and product of f and g are defined as follows. For all x, f plus gx equals f of x and g of x. If two functions are given, you can add separately. And similarly, you can multiply f of x and g of x, right, as the product. Now here I have taken an example. F of x is 3x plus 1 and g of x is x squared. Now if you are asked to find f plus g of x, you can add, now here there are no x squared plus 3x plus 1. If you ask to multiply, you can multiply x squared with this, then it will be x to the power 3 plus x squared. Now there are various types of functions. Constant function. A function of a into b is called a constant function. If the same element f of x is a member of b is assigned to every element in a, then a implies b is a constant function. If the range of f consists of only one element, function f be defined by the diagram x, y, z, w is a member of A. 1, 2, 3 is a member of B. So in a diagram, you can put x, y, z, w and 1, 2. But now all these things go to 3. So it's known as a constant function. F is a constant function since 3 is assigned to every element of A. Right? Then other types are identity functions. Let A be any set. Let the function f such that A goes to A be defined by the formula f of x equals x. Now here you can see whatever value comes here, it comes here also. Let f assign to each element in A element itself. Then f is called a identity function. Now here you get 1, 2, 3, 4, 5. Similarly, after the process, you get the same elements. Those are known as identity functions. Then types of functions. Equal functions. Two functions f and g are equal and we write f equals g. That means conditions for equal functions means functions f and g are defined on the same set D and have same domain. Functions f and g have same codomains. That is, f of a will be equals to g of a for every element of D. The types of functions, set function. F is a function of E into F and let A be a subset of E. That is, F such that E goes to F and A is a subset of E. F of A is defined to be the set of image points of elements in A, that is F of A x such that F of A equals X, A is a member of capital A and X is a member of capital F. So therefore the whole image set is a subset of F. A is a set function. Its domain consists of sets. Now I will not go to do this products and composite functions today. Here types of functions, product function. We can get a new function by the use of two already known functions. Associativity of product function. If A goes to B, that means this is the domain, this is the codomain, and G is B goes to C. Then if we define a new function H as C goes to D, then we can form the product function G naught F, means A goes to C, and then the function will be H naught G naught F, A goes to D, then H naught G of F is A goes to D. So here I will stop now, and I will do the balance. These things also I can say 1 to 1. That means from one domain, it goes to a one codomain. No two arrows goes to the domains. These are known as 1 to 1. And the other one is onto. That means each element of this is mapped to some element of this. So all have images here. This 1 to 1. This is known as onto. Other one is if they have both the properties, we call it bijection. That means it is 1 to 1, also onto. Properties of functions continued. Composite function. These composite functions I will do for the next day school, because you have to get an idea about the composite functions, and for the next day school I will do the composite functions. Okay, now I will stop from here. So are there any problems from the first day school? So I will stop sharing. How many are there? There are 42. Did you put your name to the chat? Right. Then for the next day school, I will do the balance. Now I will leave. If there are any problems, you can contact me.